All right, go ahead.
All right. Thanks everyone for showing up for the first talk of 2025. My name is Vinny Jodoin, and I am a graduate student at the University of Tennessee. And with me today, co-presenting is Brenna Kelly from the University of Utah. And this project is focusing work that we did over the summer of 2024 under the supervision of Dr. Heidi Hansen at Oak Ridge National Lab. And we're going to walk you through how we used classroom data of modality from the CDC to develop from spatial to spatiotemporal models for COVID-19. So some of us might be thinking, why does this still matter? COVID was almost 5 years ago, if you can believe it. I was at the time teaching in the classroom, so learning with my students how to teach math lessons to high schoolers on Zoom, which was a great experience. But in this case, for why we want to still look at it is that it was declared a pandemic, and this was already after there were hundreds of thousands of cases confirmed. Almost every country had it, and we were seeing significant deaths globally. We also like to look at this because it was so rich in data. And so it's helping us build these proof of concept models now with all the data that in the future, we hope to be able to apply them to other types of disease or infections that are commonly modeled. So this is really good to get models started, in our opinion. And so this is kind of how we're working with the COVID data too.
Right, so we found that a number of studies analyzed environmental exposures as risk factors for COVID-19 spread. And our ultimate goal, like Vinny said, is to be able to predict how risk factors lead to future spread, because in future pandemics, this may help us triage patients to different hospitals to avoid overwhelming our healthcare system. So in our project, we are leveraging spatiotemporal methods to build up complexity, helping us deal with this vast amount of data and diverse variables.
So to start, for any good model, you should have some sort of data collection or data file. For us, we called that our analytic file. And our analytic file, we had to collect COVID case data for the US, and we did so using the Johns Hopkins COVID data source. And then we wanted to have some sort of factors that we could use to impute the case count. And so we looked at school closure information, in particular the modality. So as some of you might recall, schools were really trying to be looked at to be opened sooner, so education didn't get stalled for so long. So some schools resulted in, if they had the means, to teach remotely. Some schools opted to teach in a hybrid session, so that would most likely look like students who were at risk or had contact with COVID cases would learn remotely while the rest of the population could still learn in building or in person. And then we also had in-person data. So we have school districts aggregated into those three categories as they reported to the CDC. And then we also had the demographic data, such as students enrolled in those districts, student or total county population, and other demographic information from the ACS.
Right, so there's this law in data science. We all probably know data cleaning takes the most amount of time of any of the processes in data science, but it always takes longer than you think it will. So cleaning this data and preparing it for analysis was a major task, especially since the data sources are no longer updated through the CDC or Johns Hopkins. So it took a little extra work to ensure we had consistent working data. We had to deal with things like negative case counts, retroactively correcting over accounts, and then preparing the data for spatial analysis. There was some funky geography as well in Connecticut and Utah, which we'll show you, resulting in us limiting our model to just 46 states in the contiguous US.
And then as our model gets updated through the maps that we'll show you. The full timeline starts from epi week 1 to epi week 164 within the data. And when we have to take into account school modality, we have to truncate that to epi weeks 34 to 154. So we lose some time scope, but we still get a majority of the time. So we're very happy with that when it came to the data cleaning. For the first state that gave us some issues, that was Connecticut. When we modeled some missingness maps just to see if there were any large amounts of data missing per state to help us with understanding state reporting at the county level. Were there just a certain counties in a state that were really bad with uploading their data, or was it like a whole state overall? This is how we determined the data quality within our analytic file. And Connecticut had everything missing when it came to school data. And I know at least one person who's graduated from a high school from Connecticut. So I know that that's not the case. So when we looked at it, we came to find out that Connecticut, out of cycle of most other states in the country, opted to change their tracking metric. And so the tracking metric that we use is called the FIPS. And the FIPS is a 5-digit code with the first 2 for state and then the last 3 for county. So for an example, Knox County FIPS code, or FIPS code as I'll call it, is 47093. So 47 is the great state of Tennessee, and 093 is Knox County in particular. So when we did the same type of look for Connecticut, we found out that nothing was matching. And within the Connecticut's state website, we found out that they were switching to things called planning regions. So they took their counties, which are shown on the map here, and they're shown with the thick lines. So you can see, for example, Hartford County all of a sudden got divvied out into 3 different planning districts: the Capital District, Northwest Hills, and Nantucket. And so within that, we had to try and determine, do we want to take the time to clean the data for Connecticut for the school data purposes, or cut the state for now? And we opted to cut the state for now and return to it when we had more time.
Right. So Utah was bigger on the map, easier to spot that, we were missing COVID data right away when we were first doing our data inspection. So Utah still has FIPS codes, we still have counties, but for sharing medical data, we used local health districts. And because, unlike the rest of the country, reporting is happening at a different level, it makes for messier data management. And so for the time being, for our purposes now, we're setting Utah aside as well.
So going to the data curation, now that we have our data analytic file slowly being developed, we currently have case counts from Johns Hopkins. We also have school modality information from the CDC. And now we're starting to prepare this after stitching all these little square patches together to slowly make this large quilted blanket. We realize that our analysis tool will require non-negative values. So when we looked at this, the Johns Hopkins data had several cases of negative counts, which intuitively wouldn't make sense to have a negative case count for COVID, and some very large negative case counts for COVID. So when we looked into it further, we came to find out that those were most likely used as corrections for case reportings, as they were usually happening right after a weekend. So we're assuming that leading up to the weekend, they were assuming what the case count would be, and then right after the weekend, they were coming back and correcting that for however they might have overpredicted. And so Johns Hopkins had a smoothing function that they had, and theirs was an interpolation method, which was taking account all the negatives over all the time and then divvying it out. And this is an issue because it's not documented well on the source on how we interface with the Johns Hopkins University. And so this is just one thing where we want to take a small moment and say that this is very common, because funding flows will usually stop when a major concern for something has move to a different issue or a different topic or aspect of the pandemic or what have you. And so currently, while doing the COVID research, there's not a lot of documentation within the data sets. So this caused us to want to try and take hold of this issue. And so we opted to make our own smoothing function ourselves. And we opted for a lag sum smoothing function. And I'll give a quick example between all of them. So let's say we have this really pretty toy snippet of data for case counts, and we have several negative case counts. Then the Johns Hopkins data would impute it. And for an example, we'll do like a mean imputation, where it'll take the average and then replace the negative values with that average. Our case was we did a lag sum. And so let's say the lag sum is 2. So we'll look back 2 case days, add those together, and add that onto the negative value. So here at 12, we would add that to the -5. That's how we get our 7. And so on and so forth. And so the imputation mean is okay because it can help with adjusting that preserves the overall trend without considering the lag data, but our method allows us to use the recent history. So this is where we're trying to take into account that we're making the assumption that the Johns Hopkins was including these negative values as case corrections. So we did want to take into account the recent history. And then for resources, we made use of the R software version 4.4, the Reich Lab at UMass using their packages on R in CRAN, which helped us interface with the Johns Hopkins COVID data. And then we made use of the R INLA project. And INLA is this integrated nested Laplacian approximation. And it's pretty new in my experience. I haven't gotten to see it. And in the next slide, you'll get to see some things that it is comparable to if you've been in the space of statistical modeling with Markov chain Monte Carlo.
Right. So if you're in this domain and you're not familiar with INLA, you may still recognize BUGS, Bayesian inference using Gibbs sampling, or JAGS, just another Gibbs sampler. BUGS is a Bayesian or full probability model, and JAGS, like INLA, is an approximate Bayesian method. So BUGS came first, and then JAGS sped things up considerably, and then things got even more computationally efficient with STAN. And we'll talk more about INLA on the next slide. Right, so then enters INLA, integrated nested Laplace approximation, and in terms of computational efficiency, INLA really blows the competition out of the water, in part because it's approximate, we're not relying on MCMC, but also because it uses a sparse adjacency matrix, so how things are related to each other. And when working with spatial and spatiotemporal data structure, this is vastly important for computational speed. And for this reason, it's increasingly popular in health studies. One issue that we think every INLA user will encounter is a general lack of documentation. So we really wanted to carefully build up our model to gain intuition about the mechanisms behind INLA. Right, so we explored several approaches for modeling our outcome, including zero inflation and modeling the spatial error, trying IID assumptions, but to really properly account for spatial autocorrelation, we modeled our spatial error using spatial random effects with the Bisag-York-Mollier 2 parameterization, which is both robust and flexible. So the spatial modeling approach was interpretable and also nicely handled zero-inflated Poisson distributions with sparse data. And it can be useful in spatial and spatiotemporal models where we want to understand overall geographic trends, but also temporal trends. This is obviously important for public health because COVID-19 spread not just geographically, but also over time.
And then to continue with the modeling talk, we employed a hierarchical Bayesian log linear Poisson model to analyze this. And unlike traditional models that use a static population, we did some really cool things with this denominator or offset term, where we took into account the population at risk over time. So we're assuming once you have COVID, you'll recover and you'll go back to being someone who could be at risk of getting COVID again. And so our population here is happening to fluctuate, where it can increase or decrease. And this allows us to have the lagged infectious period. So then that way we're allowed to cycle through. And this is where we'll call this offset term, or this denominator in our model, this delta population. So there's some amount of change happening. And this allows us to handle, in a sense, the real world dynamics for the disease, and allows us to have a somewhat more accurate model.
We've brought up spatial and temporal dependence for an autocorrelation a fair bit. So before we dive into our mapped model results, we wanted to talk a bit about what this means. So the first law of geography is that near things are more related than far things. So a county in Nebraska tends to look more like other counties in Nebraska than counties in California. It's the same thing is true in time. The weather today looks more like the weather yesterday than a day in August. So this violates the standard statistical assumption of independence, and the errors in our model will be correlated. So this is the spatial and temporal structure is called autocorrelation, and in cases where this exists, the error structure must be modeled. So in time, in the figure at the top, we're dealing with only 2 dimensions, forward and backwards. So it's easier to define observations or time windows which are related to each other. But in space, we need to create a neighborhood structure like you see on the bottom there. And far and away, the most common approach to do this is called a queen's case. And that's, what you see here. It's like a queen in chess. An observation is related to counties with which it shares an edge or a corner. And with the BYM2 parameterization we've mentioned so much, the error in a county is conditioned on the error of its neighbors. So that's how we deal with that structure. So like we've said, we've slowly built up complexity, and here is what we call an aspatial model. We're dealing with counties with an IID random effect, which are also called frailties in some disciplines, but we're not dealing with the spatial structure or neighbors of counties. We do know the structure matters, and you can see pretty plainly here. On the right, we have the relative risks, and on the left, we have the random effect of each county, and there's substantial clustering of highs and lows. So our goal as we move forward is to account for this variation with spatial modeling so we can draw inference in an unbiased manner. For instance, to understand how school modality affects risk of COVID spread.
Building up from that null model, notice how before we're going again from that full time window from 1 to 164 for the epi weeks, now we're truncating it down to the 34 to 154 as we're handling the school factors within this case. So we're taking into account the remote schools, the hybrid schools, and then the in-person is what we're leaving out, and we're using that as the comparison reference group. And then we have this offset population. And so we see, again, there's a significant difference between them, between the random effects and then the relative risk. And so we're seeing that there's large clustering here in the southeast, sorry. And so we're wanting to look into what would happen if we did start to take into account time, but also space in a more serious manner. And so we take one extra step and we take away the hybrid and we leave it just as remote. So now in a sense of a leave one out, we're taking remote and we're comparing it to that of in-person and hybrid. And so we see that the precision mean does go up for the FIPS, and we're still within our school time window. And then this is where we finally start entering into the BYM2 model framework. And so we're starting again with just a null situation. So we're not looking at anything with the school related, just the county. And so we have our mean precision for the FIPS. And we're measuring the model fit with WAIC. And WAIC is similar to that of the AIC metric for those of you who are familiar with. And so what'll happen is you'll get penalized with how complex your model is. And this is somewhat similar to the BIC, which also can penalize your model depending on complexity. So these are just very commonly used model fit metrics. So for us, we're using the WAIC. So we're seeing just this null model. This is our starting metric. And then as we step through and we add in time for the week number, we already see that our WAIC decreases significantly. And we want to minimize the WAIC for an optimized model fit. So adding in time shows good improvement to the model. And then when we add in the remote school, so we skipped going over hybrid and remote. This is just going over remote. So we're comparing remote with the sum of in-person and hybrid. And we see also that the WAIC gets minimized again. So we went from 401 to 400 for that leading term. So this is showing to us that we are, in fact, capturing more aspects of the weekly cases within our model using BYM2 as measured by the WAIC.
Right, so we've compared models using the WASC as we've built up complexity from aspatial to spatiotemporal and spatiotemporal to school modality, and we saw that our model fit improved. And this allowed us to account for in-person, hybrid, and remote learning without bias from autocorrelation. And our model was able to capture spatial and temporal dependence to improve its accuracy. So we will continue to develop this model, incorporating other drivers of infectious disease transfer like travel patterns and employment in high-risk occupations to drive forward our goal of forecasting disease spread to improve healthcare outcomes in future pandemics. Thank you to our host, the National Institute for Modeling Biological Systems.
And thanks to our sponsors, Oak Ridge Lab, Oak Ridge Institute for Science and Education, and more specifically, the Education Collaboration Program. And that's it.
Thank you guys so much. Now we will open it up for any questions. Feel free to ask.